I had to fill in for Laurent at the very last minute, so I'll try to do my best to explain mostly his work. I could say that 10% of this talk would be my contribution, and 90% is his work. So I'm trying to do my best. Stop me if you don't understand something. Not anything, I hope. And if you have questions, I hope I will be able to answer them at my best. OK, so this talk is about small width and low distortion embeddings. And essentially, it's quantized compressive sensing. I hope you're familiar a little with the context. This is a joint work. Well, the paper to which the end of this talk refers to is a joint work. But again, most of it is Laurent's work. OK, so what we will see in this talk is, well, firstly, a recap of compressive sensing, just to agree on the notation and on a few important aspects that we want to emphasize. And in particular, we will focus on random projections and what happens when you quantize them. So what happens when you apply a quantization operator that is here just a scalar quantization, but we will see it later. OK, saying what quantization is, we will move to locality and quasi-isometry, which are just two ways to understand more or less what happens to the geometry of the transformed, essentially of the image of your signal under your usual random projection when you quantize it. Locality is a weaker property that will eventually help us in assessing how good is a consistent basis pursuit, while quasi-isometry is more related to the RIP, the restricted isometry property, as I think most of you know it. OK, so just for a recap of compressive sensing, I'm sure you've heard this a number of times. What we want to do with compressive sensing is to generalize the Shannon-Nyquist sampling paradigm by, instead of taking regularly, uniformly spaced samples, for example, in time, to ask a few linear questions, which means projections, about an informative signal. And by informative, of course, we mean structured, which is either sparse or low rank. For example, it could be a low rank matrix. It could be structure sparsity. Essentially, you put your low complexity model in, and more or less an established theory can tell you if a recovery is possible from a few random projections. So I'm sure this is also pretty popular. In compressive sensing, what you do is you take a signal that you for example, let be sparse. It is here it is discrete, but it could also be. There are cases in which you can generalize it to continuous models. Then you play a sensing model, which essentially performs the duty of a sensor, and up to some additive noise or quantization noise, which is which can be modeled as additive as well. We gather some observations, which are hopefully m much smaller than n, depending on the complexity of the object we have on this side. And so again, each of these measurements is obtained as a scalar product between phi I, which is just one row of that matrix, and x, which is our signal. And why does it work? That is, why, in which cases can we say that x is identifiable or recoverable from phi x, so from its lower dimension projections? And OK, so this is just basically the basic theory of compressive sensing that I'm recapping. You take two k-sparse signals that could be, for example, in a union of k-dimensional canonical subspaces. So let's say that you take x and x prime in the set of k-sparse signals, at most k-sparse signals. You can show that for many random constructions of phi, for example, Gaussian random matrices with IID entries, sub-Gaussian, one case is Bernoulli, or even structured at times. And if you take m, so the number of rows that is increasing with k log n over k, then with high probability, the geometry of the image of sigma k under phi is preserved, which means essentially that if you have, for example, the some pairwise distances in sigma k. These are preserved up to a distortion in phi sigma k. And so, unsurprisingly, this is essentially the restricted isometry property, which means that if you take a signal u and you project it, then you will essentially preserve its norm up to distortion that depends on rho, which is the restricted isometry constant, which you can, well, you cannot calculate it because it is very complex. It has been shown to be NP hard. But essentially, for some random matrices, you know that this is well behaved. OK. So, and still with a review of compressive sensing, we know that we can recover a signal with basis BPDN, basis positive noise. So basically what we will do is enforce, what we typically do is enforce sparsity on the solution, subject to the fact that the solution verifies a data fidelity term up to epsilon, where epsilon is typically tuned to match the level of noise that you have in a signal. OK. So what we know about this program that we are going, that we typically solve, this convex problem, is that if 1 over square root of m phi, well, this notation is due to the fact that phi here has unit variance entries, and so we rescale it in order to agree with the usual restricted isometry property. So if 1 over square root of m phi respects the RIP, then if this rho is smaller than square root of 2 minus 1, we know this from the celebrated pairs of Candace. Well, we know that the accuracy of the returned estimate will be up to a constant, upper bounded by one term, e subscript 0 of k, which depends on the error in the signal model, that is, on how not actually k-sparse is your signal, and another term that depends on the amount of noise, of bounded noise, that you have on your signal. We will actually come back to this because this is actually where the core of the talk begins. So which matrices do we actually choose to perform random projections? The first one, at least historically in the theory, was a Gaussian IID sensing matrix with unit variance entries. But it has also been shown that random sub-Gaussian ensembles work. For example, Bernoulli, bounded, or ternary, minus 1, 0, and 1 with different probabilities. Not only that, there is a bulk of recent work that is more interested in fast constructions, that is, constructions in which at some point you have a fast operator that you can compute in n log n. For example, random Fourier or Hadamard ensembles. For example, random convolution. And sometimes you also use a spread spectrum operation, which is just a diagonal matrix with random plus and minus ones, so random signs, to make the performances of your sensing operator better. For example, you can combine spread spectrum with random Fourier, and you get better performances. OK, actually, this is a review that you can definitely find in the book of Foucault and Rauhut. And it was just basically to agree on a few principles. OK, why do we like random projections so much? Not only because we can process sparse signals, but also because in general, they perform particularly well when we embed other low-dimensional signal sets. As examples, we could take a finite set, which is, for example, the setup of the Johnson-Lindenstrauss lemma. So a finite set of points in Rn. We could take the set of k-sparse signals. We could take compressible signals, also low-rank matrices, and this is particularly interesting, you can also take the convex hull of the previous sets, and essentially this will still hold. The properties of the embedding will still hold. I'm going to come back on this on a second. So intuitively, the dimension of the embedding should be proportional to the effective dimension of the set. So that is, if you have a low-dimensional signal set that is not so low complexity after all, you will have to tune the the number of rows that you collect, so the number of measurements that you collect, depending on the complexity of this set. The problem is how to measure this dimension, and there is a bulk of recent work that uses the Gaussian mean width. What is the Gaussian mean width? Well, mathematically, it's the expectation of the sup over all u in your low complexity set, where g, the expectation, of course, is taken with respect to g, which is an IID Gaussian random vector. And what this geometrically or intuitively means is that you pick a random direction in Rn, you sandwich your set between two parallel hyperplanes, and you measure the width. And you essentially you rotate your set in every possible way, and you compute the mean width of this. Okay, here there is a normalization. So what this history I just told you is the spherical mean width, but up to a key random variable, which is the norm of g, you can always remap one to the other. So essentially, this mean width allows us to compute the complexity of the low complexity sets that we are looking into sampling. And there are a few examples. The squared Gaussian mean width of a finite set is log of the number of points, which remembers us essentially the Johnson-Lindenstrass lemma. As for the L2 ball, of course, we can't do better than n. But for k-sparse signals, and this is particularly interesting, this is k log n over k. And so there are commas because this is not exactly a proper definition, but you can find these findings are essentially related to the work of Chandrasekaran on the convex geometry of linear inverse problems. And here, essentially what we can show is that with very high probability, given 2 points in your low complexity set, the proximity of the points is preserved in both senses. So basically, if you have neighboring points in their ambient space, you will have that their images under phi are also close, if m exceeds the square of the Gaussian mean width. And this allows us somehow to generalize the usual RIP condition to other low complexity sets. Okay. What is the consequence of this? If you can preserve the geometry or the distances, then this means that essentially most methods that rely on proximity, so classification, SVM, nearest neighbor search, will also work in a lower dimensional domain. Okay, and there are, in the context of compressive sensing, in the specific context of compressive sensing, there is a very interesting work by Bandera, Mixon, and Recht, which is called Compressive Sensing and the Rare Eclipse Problem, in which essentially you can show that L2 balls that are separated in a high dimensional domain will remain separated if this M is sufficiently large. And of course, one question that will actually be the end of this talk is what happens if we quantize this? Okay, so let's move to quantization. I probably have been a bit slow on the introduction, as you probably are familiar with compressive sensing. Let's go to quantization. So what a compressive sensing theory says is you should linearly sample a signal at a rate which is a function of its intrinsic dimension. But what a sensor designer will say, and since I'm an electrical engineer, this somehow rings a bell, is, OK, you need to quantize it first, which means you have to fix a range and an accuracy for your quantizer. Here we will mostly deal with accuracy. In particular, we will deal with scalar quantization, which is just, essentially, it's a mapping of Rm into a regular grid of width delta. So delta is the accuracy of our quantizer. Of course, the higher the delta, the worse. Actually, one-bit quantization is a model that is related to this, but we will not deal with one-bit quantization in this talk. There are many other methods to quantize compressive sensing measurements. For example, sigma-delta quantization, as in the work of Kramer, Saab, and Gunturk. Vector quantization, or universal quantization, which is a work of Petros Boufonos. But here we will just focus on scalar quantization, and we will try to understand their geometry, as they're probably simpler to deal with. OK, so what happens if we quantize some compressive measurements? In first instance, it could seem that if we apply scalar quantization, we could just model Q as phi x plus n, where n is essentially a quantization distortion that is noise. Noise related to the amount of quantization you have. And we know from, by applying directly the previous theorem, that BPDN is stable and robust, which means that if we take some bounded noise, bounded by, in norm by epsilon, and if 1 over square root of m phi is RIP, then, of course with this bound, then this still holds. The problem is what we put in this epsilon. And actually, if you, for example, take the relation between the L2 and L infinity norm, since in L infinity that noise is bounded by delta divided by 2, which is just half the quantization bin, then if you plug it inside here, you will see that there is a square root of m that cancels with the denominator. And so apparently, it would seem that the error does not decay with the amount of the resolution of your quantizer and the amount of measurements that you add. So basically, it would seem that if you add another row to your measurement matrix, you do not get any improvement, at least from this rough model. OK, so indeed, it would seem that we have delta, where we would actually like to have 1 over square root of m, 1 over some power of m. OK, so apparently the quantization error does not decay with m. The solution to this is being consistent, which means that when you observe and quantize, and when you get quantized measurements, you have to enforce in your algorithm that the quantized representation of the quantized image of x of your candidate solution must match the one of what you have received. So this consistency condition is not guaranteed by BPDN. And at the end of the talk, we will actually move to an algorithm that enforces this. OK, why is this consistency so important? To see this, we will have to move to the concept of locality and also address partially what a quasi-isometry means. OK, so we are taking a sub-Gaussian phi. We are taking a quantizer of resolution delta and a dithering xi, and note that this dithering is uniform in the range, in the least significant bit of your quantization. What this means is essentially that you're introducing a random variation. It's no big deal. Actually, this is used in a number of, for example, in digital audio. But mostly the reason why we introduce it is because it simplifies the mathematical proofs. So, and this xi, of course, will be known to the decoder. Okay, so it doesn't really behave. It serves the purpose of noise, but it doesn't really behave like noise. It's mostly a mathematical device for the proofs. Okay, so the first property that we acquire to our sub-Gaussian random projections is that, quantized sub-Gaussian random projections, is that for each pair of points in kappa, in our low complexity set, if their images, quantized images under A, are coincident, then if they are equal, if they have the same, if they're represented by the same binary string, then it must mean that these x and x prime are close up to an epsilon, which decays as the number of projections you take, the accuracy of your quantizer, the complexity of your set, and the dimension of your ambient space. So just for a geometrical intuition, we take a low complexity set kappa. Here it's the L1 ball. Then what one of these random projections mean, quantized random projections means, is that we fix a direction, okay? And then, since we quantize it, this means that you have a bundle of parallel hyperplanes that correspond to the quantization levels apart from that are separated by one another from by delta, which is the accuracy of our quantizer. And if you add another one, you can start to see that the ambient space of the signal gets tessellated. And if you add many other ones, you will have that to each of these cells, there will be a quantized image corresponding to them. So essentially, each of these cells is mapped into a single binary or b-bit string. So the point is, the size of this should decay with them. The more measurements we collect, the more the size of this cell should decay. And this is somehow, I guess you see where I'm going. We will use this property to to show that the recovery algorithm is capable of a decaying behavior with respect to the amount of noise that you consider. And note also that in the ambient space, we are assuming a low complexity model. So it's not just any points in Rn. Okay, how am I doing with time? Okay. As for the second property that we require, note, this is a weaker property. We are saying that if two signals have the same quantized representation, then they are closed. We're not saying the converse. We're not saying the converse in the sense that we cannot say that if two signals are closed, they have the same representation, at least not in this, with this property. This is a stronger requirement, which is a quasi-isometric embedding. And what does this mean? That if you take 2 points in kappa and you look at their quantized representations and you look at how close they are, of course, close means defining a distance. Then, if they are close, we want to be able to say in both senses that x and x prime are also close in their ambient space. However, this is much trickier because first, you have to define a distance in this space. And then you have to see how this distortion, the distortion due to A, affects this transformation. And this will be much trickier. Okay. Any question? Okay, that's far. Okay, what can we say? This is a result. What can we say for Gaussian sensing? We can say that if we take phi to be an IID random Gaussian matrix with unit variance entries, and we define A as the sensing model, which is exactly the same as the previous slide, then in all generality, provided that M exceeds a quantity that depends on, up to a constant, a quantity that depends on the Gaussian mean width squared, which is the complexity of our set, and 1 over epsilon power 4, where epsilon is the error that we will allow, then with very high probability, that decays exponentially with M, and uniformly for all points in kappa, this means that if AX1 is equal to AX2, then if they have the same signature, then they are close up to epsilon. And you see here that that epsilon decays as 1 over M power 1/4, which is essentially a bad decay. This is not exactly a good decay again. This means that for one note, kappa is here any kappa. We have not specialized it to sparse signals. Okay, this is in all generality. So the proximity up to epsilon is essentially decaying M power minus 1/4. For a consistent reconstruction, consistent means that indeed you say that AX1 is equal to AX2, which means that indeed if we receive a set of quantized measurements and we have to enforce this condition, we will end up with this decay. And this is what we will observe. In the k-sparse case, it will be better, but this is the decay we observe. For the special case of sparse vector sets, this M decays as kappa, essentially kappa over epsilon, which is much better. This means that for k-sparse signals, you can say that this epsilon is an O of M power minus 1. So yeah, this for sparse vector sets and low rank matrices, you can see that this behavior is better. Okay. For the sub-Gaussian case, of course, it's trickier because, as for example, if you know a bit about one-bit compressive sensing, it has been shown that two sparse signals cannot be well recovered when your matrix is sub-Gaussian. The classical example is if you take phi to be a random signs, plus and minus 1, and if you take a two sparse signal, and there is a counterexample, a very simple counterexample that allows you to see that you will never be able to recover a two sparse signal. So there is an implicit condition also with higher resolutions that essentially depends on the nature of your sub-Gaussian matrix. So essentially we have to require that for a kappa 0 that is increasing with a constant that depends on your choice of phi, that constant is 0 for Gaussian matrices. So essentially, the constraint is inactive when you're using Gaussian matrices. But for example, it scales very badly for sub-Gaussian, for Bernoulli. For Bernoulli, you have something like, it should be square root of 27 times 9. So that behavior is really somehow limiting the sub-Gaussian case. So we take this set, which we call AMGIS, which is just sigma reversed. And we require that for each signal that we consider, its infinity norm should be bounded by the 2 norm divided by kappa 0, essentially. So this means that you cannot have a too peaky signal. You cannot have a signal that is extremely sparse. This is somehow a constraint on the minimum sparsity that you can consider. Then we have still with an overwhelmingly high probability that your consistency implies, with essentially the same rate, proximity of signals in their ambient space. So this still works, but not for 2 sparse signals. And again, this means that in more, I would say, engineering terms, the peak to average ratio must be constrained. Okay.
You have the same estimate for capital M?
Sorry?
You have the same?
Yeah, exactly. The decay is exactly the same. What changes is just you add this additional condition on the set of signals that you're allowed to consider. Okay. Note that, of course, this anti-sparsity condition was already present in earlier observations on 1-bit CS, for example, Lapanowski et al. 2014. But if this constraint is a problem for you, you can always consider to rotate the signal in another basis in which this peak to average ratio is not so bad, and at the same time apply the adjoint of that of u, so that basically phi and it's phi times u transpose is still sub-Gaussian, and this is of course a consequence of the rotational invariance of sub-Gaussian distributions. It could. If you're lucky enough to find a basis that allows you to rotate in one in which you don't have this peak to average ratio limitation, basically you will have to see the trade-off between the sparsity that you have in the rotated basis and the meeting of this requirement. Note that this constraint does not necessarily apply to sparse signals. Also, we have said that this holds for low complexity sets that have that square Gaussian mean width. It's not necessarily for k-sparse signals. But of course, for k-sparse signals, it decays better. Okay, so the epsilon decays as 1/m. Okay. This said, we can move to, okay, we have talked about what consistency means in terms of perceivability in the ambient space. We now have to deal with the second requirement, that is quantizing the RIP, which means if we recap the restricted isometry property yet another time, then we have that for all u and v that belong to sigma k, we essentially are able to preserve the distances, the pairwise distances between, for example, k-sparse vectors. But what happens with quantization? And why do we want to quantize the RIP? Firstly, because it will allow us to give some recovery algorithm guarantees to leverage approximate isometries, for algorithms that leverage approximate isometries. And secondly, because since classification, regression, and other signal processing tasks can depend on the preservation of the geometry of sigma k, then this might be a good being able to apply a quantized version of the RIP would be a good tool to explore the possibility of the accuracy, actually, of these tasks, these learning tasks. For example, related to the first talk of this morning. Okay. So let's retake the same sensing model, and with dithering, of course, and with a Gaussian phi. A naive way to bound this would be to just apply the quantization law and essentially bound it in an L infinity sense, which means that you will do the worst that you can, because essentially you will bound this by indeed, as written above, by the quantization law. So you will have two additive losses, you see minus delta and plus delta. and 2 multiplicative losses, let's say, which means that you will have a multiplicative error, a multiplicative distortion on your distances, which is which is closer to the concept of the RIP as usual. And apparently, there is an additive error, which is which further distorts the distances, and this additive error does not decay with m, apparently, at least with this approach. So it would seem that even if we increase the amount of measurements, we are not able to tame this this additive term that still occurs in this relation. And the underlying problem of this is the choice of distance. So, of course, what we will have to do is change the distance in this domain. And the choice is pretty intuitive. We just take the L1 distance of the quantized representations of u and v under phi. And what this amounts to is counting the number of hyperplanes that separate u and v. So essentially, every time you have a projection, you have a bundle of hyperplanes with a random orientation depending on the choice of phi. And when you measure the distances, instead of, think of delta equals 1, for example, which means just integers. You're just counting the distance between 2 integers, okay, which corresponds exactly to the number of planes that separate u and v. So we just changed the definition of distance to be able to prove what is the actual decay of the additive term. So again, our concern here is being able to show that the decay delta decreases as a function of m. Exactly, that the additive term decreases. So this is another result that you can find in Laurent Jacques' paper in 2015. Given an error epsilon that you fix between 0 and 1, and given kappa, which is your low complexity set included in Rm, if m is such that it increases as epsilon power minus 5, which is, yes, a bad scaling, times, again, the squared Gaussian mean width of your set, then you can show that the L1 distance between the 2 signatures is bounded from above and from below by some terms that depend both on epsilon. And epsilon here scales. It scales very badly because it's 1 over m power 5. Power 1 over 5. So it is a really bad decay in all generality, for all k. But it still scales, and it scales, and it affects the multiplicative distortion as well as the additive distortion of the distances. Of course, this result is with very high probability, and yes, all distortions decay with m. For k-sparse signals, you can show a little more. There is a typo there. It's not a, it's psi. But you can show anyway that the decay in that case is 1 over epsilon power minus 2. It's epsilon power minus 2 times k. So the decay is a little bit better for k-sparse signals. So I will not go into the proofs. If you want, you can find them in the paper, indeed. The extension to sub-Gaussian matrices is still possible. The problem is that the multiplicative distortion will have a worse behavior, essentially. So for sub-Gaussian matrices, you will see that the distortion is worse. OK, let's put all this theory into an algorithm and see what happens. So we have devised this algorithm called consistent basis pursuit, which is essentially a variation on basis pursuit that just considers consistency as a guideline for recovering the measurements. And to do so, well, we first introduced the atomic norm, which is just a general definition for a norm, so that up to an s greater than 0, you can say that your low complexity set intersecting the L2 ball is included in this set, which is essentially defined by the atomic norm, intersected still with the L2 ball. So this is exactly for k-sparse signal, this is exactly the L1 norm. And for low rank matrices, this is just your nuclear norm. So it's just a general definition, but it specializes directly into 2 very well-known examples that I guess everybody knows in this room. So given this choice, what we apply is this convex optimization algorithm. Of course, the atomic norm there is convex. what we do is minimize the atomic norm of u, subject to the fact that the AX0 is what you have received from, for example, from your sensing device, for your quantized sensing device, and you enforce the consistency of that with your candidate solution u, with u also being in the L2 ball. What that constraint means is essentially an infinity constraint, an L-infinity constraint, so it's essentially a box constraint, which means that both sets are convex, and as you can, this is also related to a significant amount of prior work. It's just a generalization with the atomic norm. What you can say about this algorithm, about solving this program, is that with high probability on Gaussian phi and uniform xi, for all points in kappa subscript s, then you can the case as some quantity that is related to the width of your quantization bin. 1/4, well, all the term there is power 1/4, so the scaling is not so rapid, but it still depends on the square of the Gaussian mean width of kappa s and m. So what you can extract from this seemingly complicated formula is that the error decays as m power -1/4. So the error doesn't, the decay still does not seem very fast, but for k-sparse signal, this is a direct application of locality. For k-sparse signal, this with the slope of -1. See that in the simulations. So for some experiments now, the implementation is trivial. More or less, we apply a very well-known parallel proximal algorithm, PPXA, or we could also apply Chambolle-Poc. We have to enforce two convex constraints subject to a convex objective. So it's the numerical part is really not particularly relevant here. You can always use this very good toolbox, Unlockbox, which allows you to devise proximal algorithms in proximal formulations of your problem in practically no time. And for some experiments, if you set b to 3 bits per measurement, then you see that with n equals 2048, kappa fixed to 16, 3 bits per measurement, and m that increases, so m over kappa is in those steps. And we take 20 trial per points, and you can see that in the black curve, you have the behavior of co-BP, so consistent basis pursuit. And in the other two curves, you have essentially the behavior of BPDN and another formulation related to the literature. And you see that the slope here is more or less -1, which is exactly what was predicted by the theory, whereas this slope is -1/3, which is worse. So this algorithm seems to work very well when you have a sufficient number of measurements, actually better than BPDN. So another remark, there is no additive noise here. The effect of additive noise at the input, so noise before quantization, is an open problem. So as for lower matrices, you can see that you can take n equal 1024 dimension matrix, which is just a rank 1 matrix. It's just an example anyway. We change the norm to the nuclear norm, and we enforce consistency. And as a result, you can see that here m equals n because of the fact that we have used a 2-bit per measurement quantization, so a very low resolution quantization. And here we can see that CoBP attains an SNR of 11 dBs, whereas BPDN only attains about 7 dBs. So we have gain in the application of this algorithm. Okay, so for some takeaway messages, how am I doing with time? 2 minutes. Associating CS and quantization does open some interesting questions in terms of geometry, in terms of numerics, and in terms of technology, most importantly. So, for example, to design an actual CS sensor, you will always have to put into account quantization. And even more importantly, quantizations do lead to interesting embedding problems, but most importantly, and I don't know if it's here, yes, it's here, for the open questions. What we are working part-time now is the effect of classification of or clustering in the quantized and compressed domain. So what we have started calling the quantized RIP problem, in which essentially we want to be able to know when, for example, two separated L2 balls in their ambient space, when you project them and quantize them, are still separated. And this is something we are working on. As for CoBP, we don't know yet if pre-quantization noise disrupts everything, and the intuition is that we could use quasi-isometric embeddings to see if it is well behaved. And finally, yeah, there are generalization, of course, of the quantized sensing model to other nonlinear sensing schemes. This could be related to the work of Recht and Boufonos on approximating kernels. And this is more, and random features, and this is more related probably to the learning aspect. Okay, and of course I am open to questions, and just to finish, we have a postdoc position open, if you want.
Any questions?
Yeah? Yeah, sure. Here, this one. U is orthonormal, of course. The problem is that if your signal is sparse but too sparse, yeah. Sure, the problem. It's essentially it's not a matter of unicity here. Actually, this proves the fact that if you have the same signature, it's not in. This is not a result about the isometry of the sensing model. This is a result on the fact that if you have the same binary signatures, then corresponding signals will be closed. It's not strictly related to the unicity of the solution. No, the example here is just that if you rotate this just enough to verify this anti-sparsity condition, then you will, this is still sub-Gaussian. Phi U transpose is still sub-Gaussian, correct? Then this means that you can essentially reapply the whole theorem to phi prime with x prime that complies with the hypothesis. Does that?
You take sparsity and then peak average ratio with that good, well-chosen notation.
Yeah, exactly. The fact that that this rotation exists, of course, it's open.
You get the same measurements with both models. And
yeah, because U transpose is the identity. It's just a way to reapply this result.
Yes, but then the Bernoulli is still a counterexample.
Sorry?
The Bernoulli is still a counterexample then because, I mean, U doesn't change the distance of two vectors. And
Yeah, it doesn't.
And you get the same measurements, and the Bernoulli example tells you that the
Yeah, but note that here we are looking at what that equality condition on the binary signatures means. It's not related to the isometry of the embedding. You see?
Yes, but the Bernoulli example is that you get the same measurements.
The Bernoulli example is that you get the same measurements.
For two vectors that are different, and if you just rotate them, they have the same distance.
Yeah, sure. I'm not saying that they have or not. Yeah, of course, they will have the same distance. You're right. It's just a device to try to apply the same theorem.
Yeah, but that example shows that this doesn't help. But anyway, okay, maybe we discuss.
Yeah, maybe we can discuss it later if you wish. Okay. That's all.
Thank you very much.
Thank you.